Our next presentation will be given by both Dr. Jay Harmon and Brett Ramirez. Brett is a grad student with Dr. Stephen Hoff. They work closely together, so Dr. Hoff decided to give the opportunity to Brett, the young scientist. Brett is a PhD student under the supervision of Dr. Stephen Hoff. He's expecting to graduate in October. His research is focused on livestock production systems and instrumentation. Dr. Harmon is an interim associate dean and director for agriculture and national resource extension and outreach at Iowa State University. His area of specialization is livestock production systems and air quality. He also provides ventilation training for swine producers. In the past 5 years, he has trained over 1,000 people, which claimed to influence the production of over 80 million pigs annually. Let's welcome Dr. Harmon.
I noticed that when they flipped up the slide that said engineer, but it went to the exit, so you know. Usually engineers don't double as motivational speakers. So I appreciate the opportunity to speak today, and it is kind of a team presentation, so I'll start off, and I'm going to talk some about the needs. Some of it's kind of more or less some laundry list and some ideas, and then Brett's going to follow up with some of the actual research that we've been doing to address a few of those things. We may throw out a lot more problems than we throw out solutions, but we're at least going to have some talking points. So, you know, I think we've made great strides in a lot of these areas in nutrition. You know, I'm always impressed with talks that John give. They're very practical and very in-depth. Reproduction, health, meat quality, management. You know, we dig into all these things in a great deal of detail, and we try to solve problems. You know, that's awesome. But then sometimes we don't pay very close attention to the environment. You know, I'm in a lot of barns where ventilation system is not operating very well. People don't have good understanding of it. You know, and to be honest, a lot of our ventilation systems aren't quite as elaborate and sophisticated as maybe they could be. So this is a common expression in engineering. Maybe it's not for everybody else, but it's a little like measuring with a micrometer, marking it with chalk, and then cutting it with an axe, right? And so we get down to the detail. You know, how many of us work very hard to balance our diets, to do a very good job with our genetics, a lot of other things, and then we kind of blow off the environment. So, you know, it's one thing that we think, a little bit, this is self-serving, we're ag engineers and that's what we work in, right? So I'm not saying that we've been slighted, I'm just saying it's a crucial part of any of these studies is when they start looking at things, they have to decide, okay, well, what environment are we going to use to test it, right? Because it makes a difference. So, so one of the things that's very important is thinking about system design. You know, and so you have all these areas, and there's probably others that I didn't include up there, that all interact. One of the real lessons for me was many years ago. In fact, I still had hair back then. We were doing some work with hoop structures. You know, trying to figure out if you can raise hoops on straw. Well, I knew from splinters from the pitchfork that I knew that we could do that. But we were doing comparisons between two facilities, and when we went to publish it, people would say, well, you can't publish this. The one group had 11 square feet and the other group had 7.5 square feet. And the environments are different. And we were comparing systems, right? So that's part of the reason why any of these kind of research is difficult, because all these things interact. And so if we were doing systems research in a true fashion, there's no way we could afford it, because we'd have to have all these facilities with all kind of different parameters, and you'd tweak this and you'd tweak that and you'd do all the comparisons, and it's very, very difficult. So the closest we come sometimes is to use some systems facilities where they're at least getting the same nutrition, and sometimes they have similar type facilities, and you know, the management's going to vary, and so it's just very difficult to compare systems. And so by rights, we investigate individual things and then hope we can throw them together in a way that's beneficial. So I'm going to cover just some topic areas, kind of go through these, throw out a few ideas, and then I'll turn it over to Brett. Some of the challenging areas include human safety. I think that's one that's been on a lot of people's minds lately. Animal well-being, of course, is always one that we're concerned with. Biosecurity, environmental, public issues, transportation, and then facility infrastructure. So I'm going to talk more about things other than just barns. But I think all these areas have some areas where we could dig in a little deeper. So first of all, you know, one of the things that we're concerned with is human safety, and there's really two areas. Is acute exposure, you know, where you have some kind of real danger situation. You know, we've had people killed, had people injured, and that's definitely a concern. We tried to do our best to warn people, to tell them the right situation, but to some degree it'd be nice to design a system where we didn't have to worry about that too much. Okay? And then, you know, there's things like foaming manure, and there's some dangers with that. We've had some of the methane fires. Barn sitting empty with no ventilation has been a problem, and so forth. The foam acting like a cap, and then all of a sudden you break that and you have a problem. So there's been a lot of work done on that. And so these are both manure pit and manure storage issues, right? So to me that says maybe that's an area that we should spend a little time on. Figure out what's the best approach to do this to eliminate some of those hazards. The other area related to that then is danger to haulers. And one of the haulers that we used to collect some data, and actually to his credit, he was doing collection before we got involved and just started sharing it with us. He had one of his workers that passed out in the tractor as he was pulling into a field. And so, you know, why is that? You know? And so what we started investigating was looking at hydrogen sulfide exposure. These are outside the barn, not inside, outside. So we already know that we have concerns when we pump. We have pigs in the barn. We try to minimize how much we stir sometimes because of that, or we listen for pigs in distress and try to vary what we're doing. And so we already know that's an issue. But these were 6 employees that during, they were hauling for over a 24-day period. They had 193 alarms go off on their personal monitoring. Okay, and these were the levels that were showing on the monitor. And so you see here we had almost 120 that were below 20 parts per million, which isn't a terrible level. It's enough to set the alarm off, but it's one to be concerned about if you were exposed to a lot. 20 to 50, we had a few less, and so forth. But you can see that there were almost 10 that hit the limit, which was 100. And 100 is a pretty high number. Now, all these are outside the barn, right? And so we're a little concerned about that exposure. Wind direction, all kind of things. Dr. Hoff and I spent a day trying to figure out different situations, and like a place between 2 barns is going to be a place where that congregates. Of course, the person with the most exposure was the one running the agitator, but the ones making all the field trips contributed quite a few to that too. So they were only exposed to the barn itself for a short period. So this is an area that we're a little concerned about. The other one related to human health then is CO with brooders. I've been in a lot of barns that have fairly high carbon monoxide. And again, you think about if the workers are being exposed to this and we're concerned, then, and it makes us lethargic, it's bound to make pigs lethargic too. So from a production standpoint, we're concerned about that. A lot of times this is related to improper maintenance for one reason or another. And we have seen some typical levels that have gone to 50 parts per million and some as high as 300 to 500. So again, that's another concern we have from a human health standpoint. So from a priority, I think improving safety while improving the environment is a big deal. One thing, I mean, this is kind of a thing that's pie in the sky. It would be nice to move the manure out of the barn, right? But that's probably not going to happen. We could start building barns that way now, and I'm not going to see the end of the ones that are deep pits that we have in operation now. Poultry has moved that way from a release, from a environmental release standpoint. They've started collecting manure outside. But that would be an easy solution. Get the manure out of the barn, we wouldn't have to worry about it. But there's cost and some other concerns about that. We have to be aware of the hydrogen sulfide during pumping. And then I think we need to look at some innovative heating systems that are less likely to produce carbon monoxide. It's a pretty dusty environment, and with the filters and some other things, it's just an issue. So this is one area that I think could use some more work. Animal well-being, of course, we've still been through some of the loose sow housing things, and I think some of that's kind of settled down. We're not paying quite as much attention to it. Farrowing crate design, I think there's still some room for improvement in that. And then heat stress in various phases. And I know we're doing some work, and I know there's a lot going on in animal science and some other areas. It was pretty interesting. I guess 2 weeks ago, I was in Morris, Minnesota, and they had some studies going where they were chilling the water into the farrowing house because they found there's some study that's out that if you're below 60 degrees, I think it is, for water, you can reduce heat stress with the sows. So they were trying that. Now, one thing, they had, they're spending a lot of energy to do that, using a small heat pump to try to chill that water. But even small things like insulating pipes might be able to help if you're not exposing the pipes to an 85-degree environment or something. Although pipe insulation is very easy to sterilize either, right? They also used some pads under the front of the sow to cool the sows, and they used the waste heat from that to heat under the creep area. So there's some innovative heat stress approaches that can be used, and I think Brett will touch on that a little bit. I think biosecurity issues, again, is very important. We've heard a lot about filtration. I think that's still a growing science area. We have some good work going on in that area. I think one of the important things to remember is that the filtered systems are not your father's ventilation system, if that's the right way to say that. There's a lot of static pressure interactions. There's lots of things a lot of moving parts to these systems that you really need somebody that's got some experience and understands the physics behind a lot of that. A lot of investment, and so we want to make sure that we do that in an adequate way. I think filtering and treatment designs, filtering is on the prime right now. There may be some other things that come up. I know there's studies on UV treatment. The problem is the retention time. You have to expose it so long, and retention time isn't very long with air in the summertime, right? And one of the things that I get into sometimes is I hear some of these systems say, okay, we have to use all this caulk to make sure that we keep our building tight. And Brett will share some information on infiltration as well. If we're counting on caulk to make our system tight, that's $1 million investment on a $4 bottle or tube of caulk. And I just have a hard time with thinking that's the best approach. We're kind of engineering some potential problems right into it. Although, you know, for years we've been saying, let's not use positive pressure because it's hard on the building shell. So using positive pressure is great from a biosecurity standpoint, but we're still evaluating what's the long-term impact on the life of that structure, and what do we need to do to make sure that that's not going to be a problem in the future. So we've got one project we're not going to talk about too much today of evaluation of filter life and pressure characteristics. And one of the things that I emphasize when I work with producers is that, you know, again, it's kind of that micrometer, mark it with chalk, cut it with an axe thing. You can filter the barn, do a great job with that part, but then if you bring supplies in some way that provides leaks, if you bring, you know, load out sows, you load out pigs, you know, a lot of thought has to go into those pieces of the system, because those are going to be the weak points. Those are going to be the points where you could get some leakage into the system. And so, you know, if you spend millions on the filtering part, then we need to make sure that we pay attention to every part, how the employees come into the barn, how everything happens. And so it has to be a total system design. You know, public issues, I'm not going to get into this too much, but they're a great influence on our practices. We heard good speakers this morning about some of these issues, and how it looks matters, right? Transportation is another one that actually, I think this is a paraphrase of a genome statement, I think, is that at no time is livestock and poultry more visible or to the public than when we're transporting it. So we have to be conscious of that and what they're being exposed to. So I think we've done some trailer work. I think there's some work that could be done in trailer design as far as reducing cold and heat stress and improve animal movement. Although when I started this study, I spent some time learning to duck under gates and things, and if you haven't been in one of those trailers, it's pretty impressive the way everything swings and rotates, and there's lots of design that went into them to make them work pretty well. But I think there's some things that we could do with improving cleanability, perhaps, the visibility again, and maybe even working on some filtration when we're transiting clean animals to a filtered situation. Secured load and unload facilities. Again, if this is a filtered facility, you have to figure out, how am I going to load those animals and still filter the air, not let the air come in through this gaping hole that I'm loading the sows out of, right? And then I think traceability of pigs, of course, is going to become a bigger issue. Facility design itself, the building shell and shell integrity is really important. And Brett will show a few slides on this. But the problem is we've had builders think that it's just a barn, right? But in our ventilation systems, it's very important that we have a structure that's pretty tight. The tighter the structure, the better the ventilation system's going to work. Because we can exchange air, but unless we exchange air in the places that do us good, it kind of doesn't help. And so we have to do a little better job with building shell and layout, and I think there's some design work that could happen there. New materials, we've got increasing animal sizes that some of the equipment probably hasn't kept up with. Building security and monitoring. LEED certification, I don't know if any of you are familiar with that, but I think it's Leadership in Energy and Environmental Design is this program that they use for buildings like this. I know the dairy farm, I think at Michigan State, had to go through this kind of certification, but it's kind of an environmental thing that some people do. Is, you know, it's kind of a gee whiz thing that a normal farm probably wouldn't do, but it's something that we could be mindful of. And then environmental control, when we get into this, you know, there's a lot of things being developed in these areas, but again, we talk about a total system for the whole facility, but then the ventilation system has to be a system as well, within a system. And so sometimes we don't spend as much time on that. Again, I'll mention heat stress, heat distribution. You know, we have a pretty crappy way of distributing heat in a barn. We put one box heater in one corner and think that it's going to travel, you know, 150 feet and everything's going to be nice and uniform. So there's some things that we could do to improve that. Some of the controllers are awesome, but some of them aren't very intuitive. You know, if a person's not comfortable with a controller, can't use a controller adequately, it's really harming them. When we do the ventilation workshops, I always ask people, how much do you pay for a controller versus the building cost? And now think about how much that controller impacts the productivity of the animals you have in that barn. So it's kind of a disproportional responsibility, you might say. Real-time sensors. I think there's going to be more and more of this, maybe early signs of disease. We had, years ago, we did a study where we tried to use image analysis to look at the posture of the pigs and determine if they were comfortable and change the temperature associated with that. You know, that probably is going to be something that'll come along as well. And this is a big one as well, and I know Brett can testify to this, is that in our systems we're able to generate tons of data. You know, you can measure the temperature every second and a half if you want to. But what does it mean and how do you handle it and how do you use that to your benefit? If you can collect data but not use it for something, there's no point in having it, right? Unless you're only using it as an alarm. Maybe that makes sense. But if you're going to use it, we need some way to manipulate it, to look at it, for it to help us manage the system more appropriately. And so I think in this day of big data, that's an area that's really going to have to be looked at more closely. And I'm going to skip ahead a little bit because I want to leave Brett some time. Of course, you know, John mentioned some of these, water distribution. I think more prescriptive delivery maybe for feed flow. Yeah, let's skip through those. I was also asked to include some concrete stuff, which doesn't really fit with the topic too much, but there was interest in it. How do you tell if concrete's going bad in a facility? And so Altenburg Construction was kind enough to share some pictures and diagrams that they had. And if you think about it, if you know anything about concrete, you know concrete doesn't have any strength really in tension, right? That's what the steel in concrete is for, is to provide the tension strength, because the top of a beam is going to be in compression. That's where the concrete works. The bottom is going to be in tension. That's where the steel works. And so you start getting these cracks and you get manure gases that can corrode that steel. You lose your strength, right? And so any kind of cracking like this is a big warning sign. There's different cracking that can occur here. It cracks along the rail. And so you get things like this where you have whole slats that fall through. And so it's important to look for all that cracking. Here's one where they've got cracking along these rails. So, you know, it's, again, that gives the moisture and corrosive gases a way to get to that rebar and corrodes it away. And then, of course, you got to realize there's a lot of concrete underneath the slats. And so if we have our column here, you're going to have some beams that may have the ends that crack like this, again, exposing the rebar, and so it wouldn't be able to bear up under the strength eventually. Or you have something like this where you have chunks of concrete that fall away, exposing the rebar. And again, that's just it's just a matter of time before that's going to collapse and look something like that. Here you can see that you know, the end on this diagram has given way and the beam has started to fall, and we don't want something like this. So regular inspections of those things are important. So with that, I'm going to turn it over to Brett. Brett's an awesome grad student that we've been very pleased to have, and brings a lot of strength to our team. So I'll turn it over to him.
Thank you, Dr. Harmon. Luckily, nobody left the room, so like the last one. So, go ahead. So I'm now going to kind of get into a little bit of my research and some other research that we have going on in our lab route with Dr. Hoff and Dr. Harmon and myself. And I'm going to get into a little bit of some precision livestock farming, or PLF. Dr. Harmon briefly mentioned about data and cameras and all sorts of other technology that's finding its way into our facility. So I'll kind of go through an overview of what kind of those technologies are and how they can be kind of useful. So first, I'm going to get back to the building envelope and talk about infiltration. Infiltration is is where all the air that is going into the building other than where you want it to go. So that's through joints, cracks, doors, curtains, holes, wherever. When we really want that air, especially during the winter, be going in through the inlets. So when it's not coming through the inlets, you're getting the cold air is dropping straight down on the pigs. We're not getting the nice rotary air movement, getting the distribution and the mixture that we as engineers had designed it to do. So that's where the envelope comes back into helping make sure that the design is fully functional, is by having the construction integrity there to help supplement the design. So reducing infiltration through the unplanned inlets helps improve the air distribution and get the behavior that we want out of the inlets. So this is a study that's been going on for several years now, and they tasked out to determine kind of where those sources of infiltration are, and then eventually get into finding out what's the most important parameters and then ways to fix those. So starting off, there's 4 different areas were tested. First was as is, or the total infiltration. That was done by using enormous amounts of duct tape to seal every inlet in all the possible locations, and then slowly reducing it down to what is the infiltration through the curtain, then looking at the infiltration through the fans, that's the shutters and the housing, and then lastly the other infiltration, the stuff that we can't see as well, through the joints, cracks, seals, all around the building. So what was actually tested, there's 17 barns that passed the quality assurance and quality criteria. These barns range from anywhere from 124 to 237 feet, anywhere from 40 to 60 feet, and a wide range of age from 2 to 23 years old. And there's some different styles, single, double wide, H-type, and an H-type that were all tested. And when you put those all together, this is kind of the main results from the experiment. So I have the standard, about the operating pressure you see in wintertime highlighted in those red dashed lines, and then the kind of the zone of infiltration across these different buildings and rooms, and sizes and ages, between about 2 and 10 air changes per hour. So to kind of put air changes per hour on more of something that we can understand, for taking a standard 1200 head finisher, about 2 air changes per hour is about 2400 CFM, or that's the equivalent of an 18-inch fan running constantly, of having air going everywhere but the inlets. So on the other side, 10 air changes per hour is about 12,000 CFM, or that's the equivalent of about a 36-inch fan running continuously. So that's all air that's not going nicely out the inlets, creating nice rotary airflow, and can cause real bad problems with air distribution and mixing. So then now looking at this to kind of split it up between total infiltration and the other infiltration. Again, we have the wintertime operating static pressure there with the red dashed line. The main thing to look here is that the other infiltration ended up being about half of the total. So that's the harder to control part, the harder spots to see, the harder spots to fix. So we see that for like total infiltration, that's equivalent for a 1200 finisher about 2.5 to 7 CFM per pig, versus on the other infiltration, it's about 0.5 to 3.5 air changes per hour, or about 5 to 3.5 CFM per pig. And for minimum ventilation being designed right around 3 CFM per pig, most of it's not going through the inlets. It's coming in somewhere else, which can cause drafts, cold spots, discomfort in other spots of the room. So kind of summarizing everything, assuming a pressure difference of about 0.08 inches of water column. We look at the total infiltration across the different rooms, ages, etc. was about 6 CFM per pig, and current infiltration was about a quarter of this. Same with the fan infiltration, right? It was about another quarter, with half of it being from the other. So kind of suggesting that for the curtains and fans are doing pretty well, except for it's the other spots that need some help. So for example, I have on there this is an example of a brand new constructed barn where they have gone and spray foamed all along the joints of the whole building. And so you can actually see it kind of leaking down here. And so this is what we're talking about with other infiltration rate, is getting these spots with spray foam and other tools to help reduce this other infiltration rate. So kind of summary of the findings. Let's look at curtains first. For curtains, with the barns that were studied with at least a 3-inch overlap, they were found to have significantly less infiltration. Same with the end pocket distance. So keeping up with making sure these overlaps are maintained and verifying that they're there helps significantly reduce that infiltration. However, what was kind of interesting is more of the age of the curtain was not significant, more of the holes in the curtain, right? Kind of makes sense. And same with the total perimeter of the curtain was not found to be significant. Moving on to the fans, this includes wall fans and pit fans. Not shockingly, the number of pit fans was significant and having more infiltration. As probably many of you know, your pump out covers are rarely looked at and tend to have holes in them, leaks, not sealed well, gaps, poor connections between the fan and the housing, and all of this is the primary cause for the fan infiltration. So other things were pump out perimeter, fan area, and total number of fans. Then kind of moving on to the building itself, what was the significant contributors? That included the width, significantly increased infiltration. Floor area, bigger buildings, higher infiltration. However, door and length were not significant contributors. So what do we need? We need better ideas, tools, construction techniques, etc., to help fix kind of these other parts, that we can't see as well. So better sealing, spray foam, improving pump out cover design and maintenance, checking, ensuring that they're well sealed. So for example here, this is a more permanently sealed pump out cover, but it's sealed. It probably does not leak. There's like a kind of a tar compound that's run around the perimeter, and this is an example of something that is well sealed that will help reduce infiltration rates. Another kind of more practical measure is during the winter. This is where the tunnel fans, there's some plastic placed around the shutters. This is a barn we were in this last winter, and it was a night and day difference in the operating static pressure from when they had the plastic on and the plastic off. It was significantly increased. And something like this, you could tell there was no draft by the shutter anymore, and it was much better. And this was pretty simple, easy thing to do. So now I'm going to kind of segue out of infiltration and into something kind of completely different. Talk a little bit more about precision livestock farming. It's kind of a term that's picked up a lot of popularity in Europe. They've been doing years of research projects on this area, and it's kind of slowly making its way to the US as we start to see more and more technology get incorporated into our buildings and controllers. So kind of what is precision livestock farming? It's really looking at the animal on an individual basis. It's making individual measurements of health, well-being, environment, behavior, everything on each individual animal. And so this kind of, I know this was mentioned earlier about robots, taking automated actions based on feedback from the single animal. So kind of what this has is it's a big cycle of looking at the animal, collecting this data from sensors, which I'll get into in a couple minutes, getting that information into a model that's either, as Dr. Harmon said, is it just an alarm, or can we do something more on prediction? Looking at all this data and coming up with machine learning techniques that can actually start to predict the onset of things, and I know there's stuff already going on in that area. Getting into that big data mining, very popular as we start to see autonomous vehicles, most of what we do on the internet's all done by this, and it's a matter of time before it makes its way into the facilities. Then actually making useful decisions is kind of the next part of doing something proactive inside the building to either prevent beforehand or help fix things. And where I'm more on the side of help fixing things on the facility is, predicting, such as knowing when a fan's going to go out a couple days before, so you don't have downtime before you can get a maintenance guy out there to fix it. Stuff kind of like that. So going through just some examples, Dr. Harmon mentioned using behavior. So for example, this is there's already a product out there on using a cough monitor that's having a microphone in the barn to detect the early onset of sickness. It's filtering out door slamming people, looking at all vocalizations of the pig, and then going through analysis, and then eventually making some predictive decision on what to do. And then eventually feeding it back to the controller in the barn to change something, or to somebody adding antibiotics or whatever treatment needs to occur. Another example, I know chickens, unfortunately, but looking at the microenvironment, temperature, humidity, air velocity at the level of the animal itself, not 6 feet above it, but what goes on there, and predicting on ways to help improve the control before something bad actually happens. Another one here is, this is pretty recent, I think in the last year, of using, there's a top-mounted camera in this poultry barn, and they're able to pick out every single chicken and use that to make decisions on, I believe they were trying to set up, putting dividers in the barn before the producer actually got there. So what they're able to do is notice the chickens had already started to divide out via the camera, so that they could know when to put the dividers in and keep them together. Back on the pig side, individual pigs with cameras of looking at behavior, aggression, things like looking at velocities, total distances moved, all sorts of data that can be collected on an individual animal from a camera. Then on kind of more of what I like to do, for example, this is the National Hog Farmer, I think last month. This is an example of I'd say an underventilated barn and a well-ventilated barn. As you see that there's a close to an 8-degree Fahrenheit temperature rise down the length of this barn, where you could say that maybe a fan might be out, or they might need to add a few fans to help increase capacity and reduce heat accumulation in that building. You also see airspeed is also low, which does not help if this is in possibly a heat stress situation, although I know the temperatures are a little low there. So versus over here, there's only about a 2-degree Fahrenheit rise across the barn, which is exceeds what we would design at, and same with airspeeds for at least the most down the barns about 2 meters per 400 feet per minute. So kind of getting more into my research that helped generate the data on the previous slide. This is the thermal environment sensor array that kind of measures more than just temperature. As the pig loses heat, more than just convection from the air around it, it loses it to its surfaces. The humidity affects evaporation, and that's due to respiration or for sprinkling. And then we have airspeed, and then lastly, the mean radiant temperature. Dr. Schwartz mentioned about pig balls earlier. This is a 4-inch plastic toilet float, and if a pig gets a hold of it, it becomes pretty fun pig ball for them, as we've found out a couple times. So kind of what kind of our plan in our research group is looking at kind of commissioning, is getting back to that kind of system view of it's not just one controller or a heater, it's all these things have to work together. And so that's getting in there with using data to kind of tease out what these different parts of the system are, how they work together, and how we can help improve that. And so that's looking at fan performance, inlet distribution, controller capability, heater distribution, comfort, heat stress abatement, etc. And so kind of switching back now to kind of the precision livestock, and Dr. Harmon touched on this earlier, of you can put the most expensive fancy controller technology that looks at every single animal, but it's got to be in a building envelope that can support it and actually supplement it. So that's kind of looking at maybe, I guess my view of looking at precision building and building design, of looking at different ways to using data and modeling and analysis to figure out how that before we actually put the animal in the building, that we give it the best chance to succeed and the technology to succeed as well. And looking at modeling airflows around, well, I know cows, but pigs, of seeing before we actually get to building the building, of how we can improve the designs in the facility. So how do we address the future? Again, system impact, instrumentation sensors are important. We don't really know until we measure it. So it's important that we keep measuring and trying to find out what's there. Value that engineering and the design behind it. We have to give everything inside the building the best chance to succeed, so we can't skip early on the building when that's kind of where the life of the animal will spend. So also kind of put a little plug in for us that there's not many programs out there producing engineers with livestock expertise. I think that's why here at Iowa State, I've had an excellent opportunity and wonderful time learning from some of the best. And I think that's why it's a great place to come here and learn kind of what we need to do to address some of these future challenges on the housing side. So lastly, I'd just like to thank Tyler Sauk for the concrete pictures, and then also the acknowledgments for our research with Iowa Pork Producers, National Pork Board, Smithfield for cooperating and letting us work with them, and Pig Tech for helping some of our projects. Thank you.
We do have time for a few questions for Dr. Harmon. Oh, and Brett. Brett, here.
Actually, a couple questions. First of all, the optical scanning technology. I had the privilege of being in Europe. Europe here, their companies marketing some optical scanning for estimating weights for sows and doing body conditioning as well as market hogs. And then secondly, in the controller world, we're kind of locked into buying products off the shelf, whereas in the industrial manufacturing world, engineers are doing specific solutions for facilities without buying a canned controller off the shelf. Are we going to get there in the livestock world where we can actually design a controller specific to our barn and not take something off the shelf?
Dude, great idea. Will we get, well, so I think working on what we have existingly is not just taking your hands off the controller, is using what is currently available, but going back to that controller after looking at data and taking that off the shelf controller and turning it into something that's customizable. There's so many settings in a lot of the controllers today that you can get to that level of customization, but you can't just follow the SOP that was handed to you and hands off. So building it ourselves may be a long time, but I think there's still a ton of work that can be done with what's out of the box and just spending time on looking at data, looking at, going through the barn, looking at pigs in certain areas and targeting individual areas and improving, tweaking parameters, over time as you learn your facility and learn how it behaves and the systems in it. So I think just working with stuff currently and then maybe get to that level of individual customization for each building, because no two buildings are alike, so the same thing doesn't work everywhere.
Any other questions? If not, we'll have a break. You can connect to Dr. Harmon and Brett during the break and come back at 3:05. Thank you.